And here's another view of looking more at the western lobe, which is this part up here. This is a photograph taken in 1903 and again in 2013. So a lot of change, right? Less snow in the landscape, less ice, and the ice that's there is much dirtier. So it has a darker color, it's melting faster because of that. And now I'm going to walk you through those changes in plan view. So again, that's the McClure Glacier on the upper left, the Lyell Glacier east and west as it was in 1883 where they were actually connected. And in this plot here in the corner, I'm just going to plot the surface area of the glaciers as a function of time. So we'll start in 1883, this is 1903, 1931, 1944, 55, 72, 1993, 2003, 2012. So if you look at that record, the first thing you'll see is that the glaciers have been retreating more or less steadily over that entire period, right? We don't see that they were ever growing and they're not even really flattening out. So there's been pretty steady retreat since about 1883 up into 2012. 2012 was the beginning of the drought. And remember, the drought wasn't just lack of snow in the high elevations, it was much warmer temperatures. So that's a double whammy if you're a glacier. You're not getting the replenishment of ice and you're losing a lot of ice through melt. So that's 2012, 2013, 2014, 2015. So a big inflection point there in how much the ice has melted now. I'm guessing that when we get up there and make the measurements in September, we'll find that things will flatten out just a little bit because we've had something more like a normal precipitation year. There's no way that it's going to make a significant change in this overall downward trend. But at first I was just extrapolating this line down, when we were looking at the loss of the glacier in about 8 years. We're to the point now, I said that the glaciers are not so sensitive to year variations, but the glaciers are so small now that they probably are going to be fairly sensitive to annual variations. Now let's talk about impacts a little bit. This is the Lyell Fork of the Tuolumne River in Lyell Canyon. Who's been there? Yeah, I figured so. Sublime place. And still a nice place to backpack up in late August or September because you've got a reliable water source in the Lyell Fork of the Tuolumne River, and that's because of the glaciers at the headwaters. So this is a photograph taken in September. You can see that there's basically not really any snow left in the landscape at all, but there's still plenty of water in the Lyell Fork, and that's good cold water that's coming from the glaciers. It's melting from the glaciers. And of course, the hotter it is, the more the ice melts, so the more water there is in the river, the more that kind of buffers the overall system. So presently, the glaciers are providing important late season water to the Lyell Fork. I want to make clear that in a normal year, the vast majority of water in the Tuolumne River is not coming from the glaciers, it's coming from just melting of snow. But especially during the dry years when all the snow's gone in the earlier part of the summer, it's the glaciers that sustain the Tuolumne River. So when the glaciers disappear, we expect that the late summer stream flows will decrease. We're going to see the water temperatures for the flows that remain probably increase, and that's going to affect the downstream aquatic and riparian ecosystems in ways that we haven't really studied yet, and we don't know the implications of, but undoubtedly there will be some. And we have now measured this. We have a pretty good sense of what might happen during the dry years late season. So this is 2013, and I'm showing you two records here from the Tuolumne River. So this is the discharge in cubic feet per second on this axis, and then from, I guess, late June to late August there. And the first thing is that the dark line is measuring the flow of the Tuolumne River in Tuolumne Meadows, right near Lambert Dome, basically. And then the lighter blue line is measuring the discharge of the river just below the glaciers, where Lyell Creek and McClure Creek come together. So that's why this is lower than this, especially during the spring melting, where you have this big pulse of water coming down the river as the snow's melting, right? So that's the pulse. Now both of these plots are dropping because the snow is disappearing. You have a couple little spikes during the monsoon storms. But once you get into mid-August here, you can basically see that those two lines converge, and I'm going to zoom in on that little spot there. Notice how the dark blue lines and the light blue lines converge. The little wiggles are out of phase because that's the daily amount of melt that's occurring, and it takes a while for the melt of the glaciers to work its way down to Tuolumne Meadows. But there are even a few places there in mid to late August where the river in Tuolumne Meadows is a little bit lower than the river is up by the glaciers, meaning that there's water being lost to the system, it's replenishing groundwater, it's being transpirated by vegetation. And so if you think about the glaciers disappearing, there's a chance that the Tuolumne River could go completely dry in Tuolumne Meadows, because right now the glaciers appear to be sustaining the bulk of the flow, in fact, maybe all of the flow during that time period. Okay, cheery stuff, I know. And believe me, I've tried to find a way to end this talk with like a great happy ending. But let me return to this plot and give you some perspective, and then we can try to cheer ourselves up. So remember, this is 650,000 years of natural climate change. And a question I get a lot is, why should we worry or care about these glaciers retreating in Yosemite if they have disappeared before in the past? And they have, right? They have disappeared before at times when those red lines were high. And I guess I would say from that very local Yosemite perspective, there will be some impacts, maybe we'll be okay. But what's driving the change is different, and we ought to be concerned about that. And we know that it's different because of these long-term records from glaciers themselves. So let me go back to the CO2 plot here, right? Notice it's low during glacial periods, it's high during interglacial periods. But the key thing, and I put those dashed lines there to show you that there's a pretty clear bound to how much the carbon dioxide in the atmosphere is fluctuating, right? And that has, again, it's all in the carbon cycle. It has to do with how much CO2 the oceans can hold, the forests can hold, the atmosphere basically can hold a lot more than it's ever been sort of cycling through. So you can see there's an upper limit and a lower limit of CO2 until about 1850, the beginning of the Industrial Revolution. At that point, we figured out a really great fuel source in terms of energy, and that's fossil fuels. So we're going to mine the sun's energy that is locked up in the fossil fuels, right? It's been in the ground for hundreds of millions of years. We have tapped it, we extract it, we burn it, and put it into the atmosphere in a geological heartbeat. So suddenly, beginning around 1850, there's this huge influx of CO2. So that's the present CO2 level way up there, right? Notice you don't see anything in the past 650,000 years that's anywhere close to that. So this is not controversial. This is just basic data, right? A big influx of carbon dioxide into the atmosphere because of burning of fossil fuels. And we know that's where it's coming from. It's not volcanoes, it's not solar activity, it's fossil fuels. The level here is about 400 parts per million. Previously, the highest was about 280 parts per million. The low down here was about 180 parts per million. So we've, that same amount that was causing changes between 2,000 feet of ice in Tuolumne Meadows and no ice today, that's the same amount of CO2 that we've added to our atmosphere at a time when the levels were already high. Okay, so that's sort of the long-term perspective on it. You can see that the temperatures have not yet skyrocketed the way the CO2 has. That's a good situation for us right now because the Earth is a slow system to respond. You can't heat it up really fast. There's a lot of water on the planet which heats slowly. But that's why scientists are so concerned, because there's every expectation that the temperatures are going to climb, especially once the sea ice melts and the glaciers start to melt, then a lot of that energy is just going to go to warming the whole system. So there is still time to keep temperatures low if we can start to bring our greenhouse gas emissions down. And as Patrick Gonzalez, who is the National Park Service's lead climate scientist, said in a talk the other day, we're in this situation because of billions of small decisions that we made along the way, small actions, and so it's possible to undo this with lots of similar small actions. However, it's probably going to be important to get some bigger policy changes in place soon to help that along. Okay, so that's basically the story I have, both of the glaciers in Yosemite, the long-term aspects of how the climate is affecting this, And I would just end, I guess, by saying that most people are never going to go to these glaciers. That's part of why I try to tell the story. For me, my attachment to these glaciers and this place is really important. I've been up there, I think, 26 or 27 times in 10 years. So I feel like I know them well and I see them change every year. So for me, oh, and then I should also say there's all this rich history of scientific research there. I'm probably the last scientist to be studying those, which is an interesting situation as well. So anyway, this is what I care about with climate change. And I know a lot of you aren't going to go there, but everyone has something that they can connect with and sort of understand how the climate is changing through their own lens or their own perspective. So I would just encourage you to find that and take whatever actions you think you can. Thanks.
You willing to take a few questions?
Sure.
Questions?
Kind of a geeky question about one of the graphs you had.
Yeah. I love geeky questions.
Yeah, the main graph you were showing, yeah, that one. So the temperature graph there on the bottom, you said something about, so the upper one comes from ice core bubbles,
Yep.
right? The bottom one comes from isotopes of oxygen. Can you briefly explain what that means and how it relates to temperature?
Yeah. Briefly?
Or not.
Yeah, no, I mean, what I can say is that in the case of the greenhouse gases, we can, and I say we, I'm not making these measurements, but I'm a scientist who tries to understand how other people do it. You can make that measurement directly. You can measure the bubble and therefore measure the gas. You cannot measure the temperature directly in an ice core. Like if you measured the temperature of the ice, that wouldn't be telling you what you want to know. But ice is composed of hydrogen and oxygen they both have isotopes, sort of like mutant atoms, that exist under certain conditions. And in the case of oxygen, there's a heavier isotope and a lighter isotope of oxygen, and the way that that's partitioned through time or across space is in large part temperature dependent. So by looking at the ratio of those two isotopes of oxygen, you can make an estimate of temperature. Yeah, hopefully that makes sense. And an important thing to say about this plot here, this particular one comes from an Antarctic ice core, but it's not the only archive of this information, right? You can see these same sort of patterns in a number of both physical and biological systems, right? So you can see it in tree cores, you can see it in ocean cores, you can see it in cave deposits, and it's basically the same sort of pattern again and again. So that gives scientists confidence that this is real. Yes, sir?
Yeah. You have a photo of yourself down a snow trench. You said you're going down to look at where the ice starts.
Mm-hmm.
How do you exactly qualify where the snow stops and the ice starts? What is the difference that you're looking for?
There's actually a pretty clean line if you're in the part of the glacier that in the previous year melted completely of snow. So if you're in the, well, for these glaciers now, sometimes the entire thing is snow-free in the fall. But if you're in the lower part of the glacier and it had no snow on it the year before, it will be dark blue, sort of gray-colored ice. And then when you get that winter snow on top of it, there's a really clean line between those. So, which is kind of unfortunate because if it's a really deep snowpack and you're trying to find the bottom, you can't convince yourself that you're there until you go all the way to the bottom and you get to the ice. And at times that's been 15 to 20 feet. We had to dig through 15 to 20 feet of snow. 2011 was the last time we had that.
Thank you.
I was just wondering why they stopped doing the measurements in 1975 until you started again.
I wonder that too. What I can say is that from 1931 to I think 1975, the team was made up of the head interpretive rangers in the park, like the chief naturalist, who would now be our chief of interpretation, would go up there for 4 or 5 days and make these measurements. And even though I know our chief of interpretation now would love to go up there for 4 or 5 days, I don't think there's any way he could do it. So it's probably a combination of time and budget and priorities. I mean, the glaciers were changing during that time period, so I don't think they just said, this is worthless work. But you know how it is. You often have to have a person who's driving that. When somebody retires or somebody goes to another park, things just sort of falter. And I suspect it was that. Yeah, thank you.
So Greg will be around during the break too, if you have any more questions. I just wanted to mention that Greg will be talking at Parsons Lodge. Greg, do you know off the top of your head your date at Parsons?
August